So that works also. Follow me? So everything was doable here because my mu x minus mu y was 0. If the mu x minus mu y was not 0, you'd do it by hand. But you would still cheat and pick up the new degrees of freedom by making believe it was 0, because the degrees of freedom is independent of the null hypothesis. Right? The degrees of freedom takes S1, S2, and N1 and N2. Yeah?
How would it look like the question, if the mx minus my wasn't 0?
So it would say, test to see if the mean cholesterol levels of case children exceeds that of control children by 10 or more, something like that. So then you know that that number is not 0, it's 10. Get it? Okay. Any question? Yeah.
So if it's like exceeding, like we can't use 0.
Right.
You can plug it into the calculator and still calculate the degrees of freedom.
Yes. So let's write it here so that it's on the video forever. If mu x minus mu y for h naught is mu x minus mu y equals 10, let's say, and HA is mu x minus mu y not equal to 10, then still get the new degree from the calculator. But the T naught will be wrong and the P will be wrong that the calculator provided. You follow what I mean? But it's easy to plug in because you're just going to go like this: x bar minus y bar minus mu x minus mu y, which is now 10, divided by rad sx squared over nx plus sy squared over ny. So it's doable. It's not that bad, right? Get it or no? And the same thing in the pooled variance t-test also. Let me go to that one and just walk you through that one. Let me go to the notes from the last time and show you what I mean on the pooled variance. So these were the notes for the last time. Let's make believe that this was not 0, but this was 10 for the pooled variance. Again, I would cheat and use the calculator, but just understand that the calculator is using 0 here and not 10, right? So this part would have to be, let me go to the right one. So in this T formula, this part would now be 10, not 0. So this would be 10 and not 0. But you can still pick up the SP from the calculator. The pooled variance, the pooled sample standard deviation. This is the square root of the pooled variance, right? So this SP value can still be gotten from the calculator. And the rest is not so difficult to plug in. So from page 3, notes from the last time, if mu x minus mu y was, say, 15 versus mu x minus mu y not equal to 15, I would do like this: T naught equals x bar minus y bar minus mu x minus mu y, which is now 15, over SP rad 1 over nx plus 1 over ny, like so. And SP, I'm going to cheat and take it from the calculator. So really the only part left for me to do is to plug into this formula where the SP is provided by the calculator. Follow what I mean? Because SP is equal to nx minus 1 sx squared plus ny minus 1 sy squared over nx plus ny minus 2. And this formula is independent of mu x minus mu y equaling 15 or 10 or 100 or what have you. So it doesn't matter. Cheat and pick up the SP from the calculator and then plug into here, but make sure you plug in 15, not 10. I mean, not 0, like the calculator does. Follow? This is for the old procedure. This is for pooled variance. T-test statistic.
Wait, is that for SP or SP squared?
SP square, thank you so much. Thank you. SP square, that's the variance. Thank you. We wouldn't want people saying you said in your notes. Okay. We have a few more minutes. Want to talk chi-square? Might as well. The more I do now, the less we're cramming next week. Okay, let's talk about chi-square. So, keep it down. So I'm done with this entire set of comparison of means lecture. We first talked about matched pairs, where the subjects come in as pairs. Then we talked about independent samples using Z. That's when sigma. Then we talked about independent samples using T. Which T? It's either pooled or unpooled based on the results of the F-test. When the F-test is significant, you use unpooled. When the F-test is not significant, you use pooled. And you use either this formula or the simpler unpooled formula with new degrees of freedom based on whether you're doing pooled or unpooled. And that's it for this whole chapter. Yeah? You good? Okay, let's go to chi-square. Oh, I don't know what page this is. I want to do a simple chi-square test. Chi-square goodness of fit. Chi-square goodness of fit test. So now we're dealing with counts. Meaning I'm counting how many people fall in a certain category. Let's say that we're testing to see whether 80% of my class is freshmen, so H0, probability freshmen, 80%, probability, what are you guys? Sophomores? Freshmen? Okay, sophomores, 5%, juniors, 8%, and seniors, 2%. So, assuming that this is what we think the distribution is of this class, okay? This will be provided to you. So that's your null hypothesis, H0. And then they give you observed counts. So HA will be the distribution is different than that provided above. And then they'll give you some observed counts. So let's say that there are a total of 200 people in our class, and let's say that the freshman count is 130 and the sophomore count is 20. And the juniors are another 20, 30 and 20, 150, 170, and the seniors are 30. So 30, 40, 50, 60, 70, and yeah. So let's say that this is what I actually observe, and I'm looking to see if there is a fit. So I'm looking for goodness, yeah.
Does it matter if like H naught is not equal to 100?
It's not?
No.
That's my bad. 80, 85, 95, 85, 90, 100. Thank you so much. I'm trying to squeeze this in and I'm making mistakes. Not good. Okay. Thank you for that. And thank you for not waiting until I'm done with the problem, because then the whole thing would be garbage. Thank you. I appreciate that. Okay. So they gave me observed counts, and my job is to come up with expected counts. So you remember your formula for expectation? Binomial, mu equals n times p. Remember that? So this is not binomial, this is multinomial. But the formula would be the same. E equals n times pi. So that's allows me to find my expectation. So let's take 200 and multiply by 0.85. I get 170. 200 times 0.85. And then the next one would be 200 times 0.05, which is 10. And then 200 times 0.08, which is 16. And 200 times 0.02, which is 4. Just check me, does this add up to 200? 20, 30, 170. Yeah, we're good. So those are my expected counts. Then there's something called the chi-square test statistic, chi-naught squared, which is summation observed minus expected squared over expected. So we're going to take the difference between what was actually observed and what was expected to see if they match up. If this number is big, it means that there's no match, because the difference between observed and expected is too big. Follow me? And then this division by E is because you want to put this difference squared with respect to the expected counts. Because if the expected counts are too small, it unduly blows up the chi-square test statistic. Whereas if the expected count is large, then this difference squared over the E could be minimal. Let me explain what I mean. Let's say that O minus E for one of these categories happens to be 10. So 10 squared is 100. If this expected count is 1,000,000, then 100 over million is minimal. But if this expected count is small, something like 100, then 100 over 100 would contribute a whole 1 to the test statistic. So that's why this expected count E is relevant. In any case, let's find this. So this is 130 minus 170 is negative 40. Negative 40 squared is 1600. Divided by expected, which is 170, plus 20 minus 10 is 10. 10 squared is 100, divided by 10, plus 20 minus 16 is 4. 4 squared is 16, divided by 16, plus 30 minus 4 is 26. I don't know what 26 squared is. 676. Divided by 4. So my test statistic is going to be huge, because already this number is huge, right? Huge. Then I go to my chi-square, which is another right-skewed distribution with k minus 1 degrees of freedom, where k is the number of categories. So here I had 4 categories. K is 4 for this problem. So k minus 1 would be 3. And the reason why the degrees of freedom is k minus 1 is because you see how this total had to remain 200? And 3 of these are free choices, but the last constraint, the last one is not a free choice because